So the field of cache memory, it's kind of an overlap between operating systems and computer science. So we know that the processor can read and write from memory. And now the idea is we want to take a look at what's involved in reading and writing from memory. And so here's kind of a schematic of, suppose we had a set of memory cells. So these fields are either set to 0 or 1. And they get grouped together. So we use the word a register when we group a bunch of bits together, a bunch of memory cells together. So this is a 4-bit register. And sometimes 4 bits being grouped together, 8 bits being grouped together is referred to as a byte, right? Have you ever heard of 4 bits being grouped together? What they call that?
Nibble.
Nibble. Okay, yeah, I thought that was from 20 years ago. I thought that went away. But so anyway, so the reason I did a nibble is because it would make the picture real cluttered if I did a byte. So this is a 4-bit nibble. This is another 4-bit nibble, the third one, and the fourth one. And if we want to read from memory, what we want to do is we put on a decoder. We have a memory address register, and we pick which one of the nibbles, which one of the 4 nibbles we would like to read from. So in this example, if I put a 0 here and a 0 here, then this decoder, a decoder, if you remember, takes binary input and has one output for every possible value the input could be. So 0, 0 would turn this wire on and these 3 wires coming out off. So a decoder turns one wire on and all the other wires on. And it's whatever value you pick here. So I'm picking 0, 0, which means I want the 0, 0 nibble, these 4 bits. I want these 4 bits to be transferred to these 4 bits. So basically, so like this represents my main memory. And this represents a register in my processor, one of the places I could capture data from. So I put a value here and a value here, and I allow a certain amount of time to go through. And there's AND gates and OR gates in this decoder, and eventually this wire turns on and these 3 turn off. This wire being on goes into this set of AND gates, and what goes into these AND gates is the value of A comes into this AND gate, the value of B comes into this AND gate, C comes into here, D comes into here. So if this wire is on, after we let the electricity flow through these AND gates, if you remember, an AND gate was made up of a NAND gate with a NOT in front of it, so this amount of time for the electricity to flow through. What would eventually come out of these wires, these 4 wires, if this one was on? So red means on, and this kind of came out green. It was supposed to be like yellow, but it comes out green. But if this one is on, what would the 4 values coming out of these AND gates be? If this wire is on.
Same value before.
Say whatever A, B, and C and D are, that would come out of here. So yeah, so I made it like blue, meaning, I don't know, it could be a 0 or a 1. If this wire is off, and therefore 0 is going into this AND gate and 0, 0, 0, and then E, F, G, and H are also being wired into here, what would come out of these ones?
E, F, G, H.
Well, no, so these are AND gates,
Okay.
and this decoder has this wire is off. So it's a 0 plus whatever E is. Sorry, not plus. 0 and whatever E is. E could be 0 or 1. So what will come out of an AND gate if you put, in the 2 inputs, if you put a 0 plus some random bit, what would come out? So this, a 0 would come out,
Yeah.
because one of them is a 0, therefore the output would be 0.
But I have a question.
Yeah.
Because you said 0, it will be off here. Lawrence?
This one, 0, 0?
Yes, it will be off.
Well, no, so, okay, so the 0, 0 here, so there's 4 wires coming out of here.
Okay.
Whatever binary value I put here,
Uh-huh.
like if I put 0, 0, that means this wire will be on, and these three will be off. If I put 0, 1,
Okay.
this wire, the second one would be on, and this one, and this one would be off. So what a decoder does is whatever binary value you put on it, one of the wires is on and all the other wires are off. And it's the value you put determining which wire is on. So it might have been better if I turned this one on, because if we could get the same principle. Well, when we're writing to memory, I end up using a 0 and a 1. So in this case, this being a 0 means take all of these values, 0 them out, and have them get pushed in here. This wire being off says take all of these values, 0 them out, and push them into here, and this one zeros these ones out and pushes them in. And these are all OR gates. So if we take, for example, what goes into this memory cell, if we put a 0 and a 0 here, then the value of A comes out of here and goes into this OR gate. And then a whole bunch of zeros go into the OR gate. So it's the value of A plus a bunch of zeros all get ORed together. So what would come out of here? The value of A. So so basically whatever number we put here, the A passes through here, the E got zeroed out, the I value got zeroed out, and the M value got zeroed out. So it doesn't matter what E, I, and M are, only A made it through this gate. So the idea is it's going to take a certain amount of time. So we're reading from memory. From the moment we put a number here, till the electricity flows through this decoder and eventually turns this wire on and these three wires off, then the electricity flows through here. This value has to run through this AND gate and a computation is done, and then this value goes into this OR gate, and this OR gate takes a little time for it to come out. So it'll take a little time for this to happen. So in this picture we have our main memory has 4 values, but if we were using a, like if you bought a computer recently, you went to Staples and bought a computer, they typically use 32-bit addressing. Some of them now use 64. Have you bought a computer lately? Okay, but a lot of them use 32-bit addressing. So if we had a decoder that was not 2 bits long, but was 32 bits long, it had 32 bits on this side, how many wires are coming out of it? It would be 2 to the 32. So 2 to the 32, 2 to the 10 is a K, 2 to the 20 is a meg, 2 to the 30 is a gig, 2 to the 31 is 2 gig, 2 to the 32 is 4 gig. So there would be a little over 4 billion wires coming out of this decoder to pick which, and then the inputs here, this would have 2 to the 4 billion inputs to these OR gate. So the point I'm trying to make is that it will take it'll take not a lot of time. It's amazing how quick it is. But from the time we set the address until the field we pick is copied into our memory will take a certain amount of time. And obviously the bigger the memory is, the more time it would take. Right? If we had a 32-bit machine and we put a 32-bit number here, picking a field to read from, it's going to take a certain amount of time. If we have 64 bits, we're going to have to allow more time. But the good news is we have more memory. The bad news is it takes more time because we have a lot more electronics. The same idea is kind of true with writing to memory. So here we have a nibble, 4 bits, and we want to pick one of these nibbles to take this value and write it to that location. So sometimes we read from memory, sometimes we write to memory. So if we wanted to take, so these letters again mean that it's a 0 or a 1. We don't know what it is. We want to write W, X, Y, and Z. We want to write those values to one of these 4 nibbles. So we put a value in our MAR, or memory address register, and this time I chose 0 and 1. So that makes this wire go off, this wire is on, and these 2 are off. So this is now, this is the 0 wire, 1, 2, and 3. So we put the binary number of 1, turns this wire on. And so if you remember when we talked at the beginning of the semester about memory, it had 2 inputs. One, if you turned it on, it would accept a new value. And if you shut it off, it would remember the old value. And it would ignore anything you're trying to put in. But if we turned it on, then that means this memory cell is open to take on a new value. And then this would be our new value. the value of W gets fed into all of these 4. So that's the purple line. So the value of W is actually being fed into all 4 of these cells, but only the one that we put the address here will accept it. Only this cell will take on that value. These 3 will stay the way they were before. So if we want to write to memory, we pick the location we want to write to. This MAR has a lot of resistors and transistors, and it takes a while for the electricity to come through, and eventually this line turns on, which then opens this thing. If you remember, inside of here was that flip-flop. We had the OR gates that fed each other, so that takes a little while for the electricity to settle. And then eventually we can shut this bit off, which would actually cause all 4 of these to go out, so that all the memory stays the way it is. So again, that step takes a certain amount of time. The more memory you have, the longer it will take. So that was, just a good topic to refresh our memory on computer architecture. So, yeah, this is just a little bit of write-up. I won't read it to you, but the idea is basically this. The bigger the memory is, the more time it would take to read and write from the memory. It takes approximately the same amount of time to read and write, because the path, both times we're setting an MAR value that's going through a decoder. Then that could either open up gates to let values in, or it feeds to a big OR gate, the value we're trying to read from. And the bigger the memory is, the more time it takes to do that step. So, the idea, but now we remember when we're talking about virtual memory, if you put pages of data into memory, sometimes the page you want is in memory, sometimes it's not there. And it got very expensive if it was not there, right? If we went to get a page that's not there, we'd have to go out to the disk drive and bring it in. So the idea is now, what's the best size of memory to pick? If you pick a big piece of memory, every time you go to read or write from it, it takes more time. If you pick a smaller piece of memory, every time you go to read or write from it, the thing you're looking for is more likely to not be there. So we have kind of a trade-off. So this is like a little silly picture, but we have a CPU. And so far we've always talked about the CPU being attached to main memory, which is memory that runs on electricity. And then main memory is connected to some kind of storage that doesn't process out of electricity, like disk drives and floppy disks and tapes and all that stuff. So anything that was not in main memory, you go out to our secondary storage system and bring a copy in. So now what we're going to do is we're going to consider the idea of having a smaller memory than main memory, and put the smaller memory in front of the main memory. So the CPU will process directly out of the small memory. And sometimes the word cache, sometimes it's pronounced cache, sometimes it's pronounced cache. Have you heard that word used not in computer science, like outside of computer science, like as a subset of a bigger thing? So anyway, so we have a cache memory, which is going to be a subset of main memory. So we're going to assume that every page of data, every block of data that's in the cache, a copy of it appears here too, plus main memory has more stuff. So it has everything the cache has, plus it has other stuff. And then the idea is that when we go to process, we're going to hope what we're processing is inside the cache. And because the cache is smaller, we'll be able to read and write faster. If it's not there, then the bad news is we spent a little time looking here, found out it wasn't there, and then had to go to the next step. If we just went to this from the beginning, we could have gotten there a little sooner. So we want to figure out if it makes sense to even have this cache. So we're going to talk about like the idea of a hierarchy of memory. So it basically just says the processor can go look to a smaller memory, and if what it's looking for is not there, then go to the next smaller one, and if it's not there, go to the next one. Keep searching, what they sometimes call a memory walk, to go through all the different levels of primary memory, which is memory that runs on electricity, until you find what it is you're looking for. Okay, so that then brings us to the discussion of the percentage of time the thing we're looking for is in the memory we're looking at. So we have the idea of a hit ratio, or sometimes they're quoted as a miss ratio, But if you go to a piece of memory looking for, you know, a variable like X or whatever, you go to memory to see if the chunk of storage you want is there. The smaller the memory is, the higher the chance it won't be there. So we'll have a probability that what you're looking for will be there. And the operating system can observe this over time. It can see how many times you went out to memory looking for something and it was there or it wasn't there. So sometimes they refer to it as the hit ratio. That's the percentage of time you go looking in memory and the page you're looking for is there. The percentage of time it's not there, which is just 1 minus the percentage of time it's there, that's sometimes referred to as the miss ratio. So the hit ratio equals 1 minus the miss ratio. So, for example, suppose we had the situation where we wanted to accessing the cache takes 2 nanoseconds. So from the time you set the address you want to read to the time the data is brought to you, or if you're doing a write, the time it takes for you to write the data there. Suppose that takes 2 nanoseconds, and main memory, which is much, much bigger, takes 10 nanoseconds. Okay, so the good news is the cache is quicker. The bad news is a lot of times what we're looking for won't be there. So the question is, what hit ratio would the cache have to have before this thing, so that this thing could be, using the cache would be considered helpful? Well, without the cache, if we took away the cache, or never added the cache, then each memory reference read or write would take 10 nanoseconds. Now that we have the cache, we're going to say the amount of time it takes to reference data would be, well, what percentage of the time is the thing we're looking for in the cache? So that'll be whatever the hit ratio is, the percentage, well, let's say 50% or something like that. So the percentage of time that we're in the cache times the amount of time the cache takes, plus the percentage of time, we'll call it the miss ratio, the percentage of time that what we're looking for is not in the cache, times, and now we're doing 2 things. We're searching the cache, and then we're searching main memory. So sometimes the cache is going to help us, right? The cache will help us when the thing we're looking for is in the cache. Then instead of taking 10 nanoseconds, it'll take 2 nanoseconds. So that's a lot quicker. But then there are going to be times when the cache hurts us. When the thing we're looking for is not in the cache, then we have to take 2 nanoseconds to realize it's not in the cache, and then another 10 nanoseconds, which is now 12 nanoseconds, if it's not there. So sometimes it's going to take 2 nanoseconds, and sometimes it's going to take 12. It used to take always 10 before we introduced the cache. Now sometimes it's going to be 2, sometimes it's going to be 12. So what percentage of the time does the thing we're looking for have to be in the cache for it to even be worth it to have the cache? So if we took, you know, the hit ratio times 2, plus the miss ratio, which is 1 minus the hit ratio, times 12, then we would want to calculate what would be the best hit ratio. So 2 times the hit ratio equals 12 minus the hit ratio times 12. And then we put the 12, you know, group the 12 times the negative hit ratio in 2 times. We'd have 12 minus 10 times whatever the hit ratio is. So when 12 minus 10 times the hit ratio is less than 10, which is how long it would take if we didn't use the cache, whatever hit ratio makes this true would be a time when we would want to use it. So as long as the hit ratio is greater than 20%, as long as what we're looking for is higher than 20%, we'd be okay. If what was in the cache is, say, 50% of the time what we're looking for is in the cache, then it would make sense to use the cache. If what we're looking for is only there 10% of the time, that would mean 10% of the time we're taking 2 nanoseconds and 90% of the time we're taking 12. We'd be better off getting rid of the cache and just doing 10 each time. So, you know, these questions would have the, you know, you're told what the hit ratio is, or you're told what the miss ratio is, and then what's the total access time, or would it be, you know, an advantage to use it, would it not?
Yeah, what is a good percentage? So to like 25, 30%?
Well, so the thing is, yeah, that's kind of an interesting question, is, when you're installing a cache, there's a trade-off. The smaller the cache is, the faster it is. But the smaller it is, the more you're going to miss, right? You're going to have a higher miss ratio. So then the question would become, and I guess, yeah, this would kind of be in computer architecture when we were talking about instructions have steps to them. You can fetch the instruction, decode the instruction, read the input, execute the instruction, and then write the results back to memory. So if we're using main memory and the writes always take 10 nanoseconds, then the write step is done in one step. But sometimes we could take the write and do it in multiple steps, like write part 1, write part 2, write part 3. And putting in a cache, the cache could be part 1. And if it's not in the cache, then we would have to use the clock cycle for part 1 and part 2. So you might want to pick a cache that's big enough to take up the amount of time for the part 1 cycle. So it's more like what we want to just get used to is the idea that the bigger the cache is, the slower the cycle is, and then because we're doing this memory walk, it would take more time to look in the cache and then the next cache. So there is no right answer. What's the best miss ratio? It's you're comparing the miss ratio to the time of the cache. You're trying to pick the best one that way. So suppose we had a choice now between two caches, a small cache and a big cache. So suppose we're considering buying one of two caches, a 32K cache, which is, it's so small it takes 1 nanosecond to read or write from memory. And let's say it has a miss ratio of 1/3. So that means 2/3 of the time what we're looking for is in the cache. 1/3 we looked and it wasn't there. We could also use a 64K cache, but because it's twice as big, it takes 2 nanoseconds to read and write from memory. But because it's bigger, it has a lower miss ratio. Only 1/6 of the time is what we're looking for, not there. And let's just say main memory takes 10 nanoseconds and never misses. So this actually saying, like in virtual memory, you bring in part of your program, and then as you're running it, the parts you don't have, you go out to the disk and bring them in. So we're actually saying your entire program is in main memory. You'll never have to, anything you ever want, in this example, is in main memory. So the question is, should we use one of these caches, and if so, which one should we use? So, so the expected number of seconds per memory reference, the expected number E, if there's no cache, would be, we're told, is 10 nanoseconds. But if we use the 32K cache, then what happens is 2/3 of the time, what we're looking for is in the 32K cache. So 2/3 of the time, it'll take 1 nanosecond to read from memory. And then the percentage of time we're not in the cache, which is 1/3, the miss ratio, we're going to spend 1 nanosecond looking in the cache and realize it's not there. And then another 10 nanoseconds looking in main memory and finding it there. So 2/3 times 1 plus 1/3 times 11 comes out to an average of 4 1/3 nanoseconds on average. Now we consider taking the 64K cache. So in the 64K cache, 5/6 of the times it has a higher, so the good news, it has a higher miss ratio, a higher hit ratio. The bad news is because it's bigger memory, it takes longer. So 5/6 of the time it will take us 2 nanoseconds, and then 1/6 of the time when we miss, it's going to be 2 plus 10. And then you do the math, and this one comes out to 3 2/3 seconds on average. So in this case, the 64K cache would be better than the 32. Even though it's slower, what we're looking for is in it more often. So in this case, using of the 3 options, don't use a cache, use the small cache, or use the big cache. In this case, using the big cache would give us the best average time to do reads or writes from memory. Okay, then there's no rule that says you have to have one cache. You could have multiple caches. So suppose we wanted to have, we were thinking of let's put 2 caches. Maybe 2 caches is better than the better of the one of the 2. So here the data is a little bit different. The hit and miss ratios are different. So let's say we have a 32K cache, which takes 1 nanosecond to read and write from, and it has a miss ratio of 50%. So maybe our program is either just jumping around so much that you know, the cache isn't doing as well. But so 50% of the time, we are in the, what we're looking for is in the 32K cache. Now, if what we're looking for is not in the 32K cache, then we'll search the 64K cache. That may happen. So the 64K cache, which is bigger, takes 2 nanoseconds and has a miss ratio of 1/4. So 75% of the time, what we're looking for is here. And then main memory, as we're walking down all our memory, the access to main memory is 10 nanoseconds and has a miss ratio of 1/10. So 90% of the time, what we're looking for is in main memory. And then 10% of the time, it's nowhere in any of our memory hierarchy, and we have to go out to the disk drive. And disks take much, much longer than electronic memory, so let's say that takes 100 nanoseconds. Okay, so what would be the expected time, on average, to go through our memory hierarchy, walk through and get the memory of what we're looking for? So, 50% of the time, what we're looking for is going to be in the small cache. And that takes 1 nanosecond. So that's 50% of the time is 1 nanosecond. Now we have to figure out what is the percentage of time, what we're looking for is not in the small cache, but is in the big cache. So what has to happen for it to not be in the small cache, but to be in the big cache? Well, 50% of the time it's not in the small cache. We go, and then it may not even be in the big cache, but what percentage of time is what we're looking for in the big cache? Well, 75% of the time, because it has a miss ratio of 1/4. 75% of the time, what we're looking for is in the big cache. So 75 minus 50 is 25% of the time, what we're looking for is in the big cache and not in the little cache. Right, and remember, the little cache is a perfect subset of the big cache. Everything that's in the little cache is also in the big cache, plus the big cache has more stuff, actually twice as much stuff. But everything in the little cache will always be in the big cache. So, this 25 comes from 50, the probability we're not in the little cache and we are in the big cache. So 75, so it'll be the hit ratio of the big cache minus the miss ratio of the smaller cache. So that's where this 25 comes from. And now we have to search the small cache plus the big cache. So it takes 3 nanoseconds every time what we're looking for is in the 64K cache. Now, what is the probability that what we're looking for is not in the small cache and not in the big cache, but is in main memory?
90% minus 75.
Yeah, actually, I probably should have wrote that out. But yeah, so it'd be 90. The probability we are in main memory minus the probability we are not here, not the level before it. So that would be 90 minus 75, which is 15% of the time. So 15% of the time, we're going to look in the little cache, then the big cache, and then main memory. So 15% of the time, it's going to take 13 nanoseconds to get what we're looking for. And then the last one, what is the probability that we actually have to go out to the disk drive? So that's the probability we're not in the 32K cache, not in the 64K cache, not in main memory, and therefore have to go to the disk drive. And that'll happen
100 minus 10, I mean,
Yeah.
minus 90. Yeah,
Right.
10.
10% of the time. So it'd be, all right, so at each level, you're looking at what is the probability you're in this stage minus the probability you missed here. So it's this level's hit ratio minus this level's miss ratio. That's the probability you're in that window. So 10% of the time, we're going to go through everything and have to go out to the disk drive. So 10% of the time, it'll take 1 plus 2 plus 10 plus 100. So 10% of the time times 113. And then you add all this up. I don't know if anyone has a calculator or Excel, but, you know, and then you just add that up, and that would give us our average. So we could try calculating it with just the 32, just the 64, none of them, or both of them, and pick the best, pick the best one. Okay, so yeah, does that make sense? So it's to get the probability that you hit that, whatever level you're on, it's the hit ratio of the level you're looking at minus the miss ratio of the previous level. That would be if you're walking through each of them. And then this topic kind of turns into, depends on which textbook you read, but there's a piece of hardware we talk about in computer architecture called a translation look-aside buffer, which is basically a cache. It's a cache memory. It's a small subset of the memory in your system, but instead of you addressing it like the nibble picture we had before, where you put an address in and you let the electricity flow through, the translation look-aside buffer is so small that you can actually take a part of the virtual address, take the page part of it, and do a bit-to-bit comparison with all of the entries in the translation look-aside buffer. And you could do this in the time it takes to run one computer instruction. You can simultaneously compare to see if the page you're looking for is in this thing. So this could be done like in the time of one instruction, not the time of reading and writing from memory. So for our purposes, we can check this thing simultaneously to checking whatever our smallest piece of memory is. So we could check the translation look-aside buffer in the same amount, while we're simultaneously checking our smallest cache. So if it's in here, then the amount of time it takes for us to write to the translation look-aside buffer, we could do in whatever time this takes. But if it's not in here, we don't have to then wait for this lookup to be finished before we can start the next one. So, and then you're right, so again, depending on the author of the textbook, they might consider the TLB to just be a very small cache. And then you'd be going sequentially through it. But what we're gonna do is we're gonna assume that anything that's in the TLB, we can search this and this cache at the same time. So, and the TLB is considered a very, very small cache. So let's say the translation look-aside buffer has a miss ratio of 4/5, meaning 20% of the time what we're looking for is in it. So the 32K cache takes, let's say, we're just changing the numbers now, 5 nanoseconds and misses 60% of the time. A 64K cache takes 10 nanoseconds and it misses 25% of the time. And main memory takes 30 nanoseconds and has a miss ratio, what we're looking for is, it misses 10% of the time, so what we're looking for is there 90% of the time. Okay, and the disk has all the pages, and the disk drive, again, takes 100 nanoseconds. So what would be the expected amount of time? So what percentage of the time is what we're looking for is going to be in this, what's now a really small cache, that could be searched using hardware simultaneously to the first level, the 32K cache. So 20% of the time, what we're looking for is going to be in the TLB. So it'd be 20% of the time times 1 nanosecond. Then what percentage of the time, and this is similar to the problem we just did before, what percentage of the time are we in the cache, but not in the TLB? So that would be 40% of the time we're in the, 60% of the time. No, where are we? Sorry. 80% of the time. 80% of the time we miss the TLB, and 40% of the time we are in the cache. So there's going to be 40% of the time what we're looking for is here, but not here. And then that'll take 5 nanoseconds, not 1 plus 5, but just 5, because this and this can be searched simultaneously. So we've begun this search while we were doing this search. So that's why this is a 5 and not a 1 plus 5. So the only difference between a TLB and a cache is the TLB is so small it can be searched simultaneously to a cache. Then the probability that we are in the 64K cache but not the 32K cache would end up being 6 minus 0.1. No, sorry. 0.06 is the probability we miss this one, And then the probability that we hit this one even though, wait, what was it? Wait, there's a 60% chance we miss this one, leaving 40% left over and 75% of those. That's right. We want to take the probability that we are in here, which is 75%, minus the probability we missed here, which is 60%. So that should be 15, right? So that should be,
Yes.
so this should be 75 minus 60, right?
Yes.
Okay. Right, so 75 minus 60 times, wait a minute, did we just miss some?
Time 5 plus 10.
Wait, this is the TLB. This is the probability that we are not in the TLB, minus the probability that we are in the cache. The next one should be the probability that we're here, minus the probability that we're not here. So it should be 75 minus 60, and the time would be
5 plus
5 plus 10. Okay, sorry about that. It should be 5 plus 10. And then the next one would be the probability that we are,
90 minus.
it'll be 90 minus 75.
Okay.
Times 5 plus 10 plus
30.
30. Okay. And then the last one would be the problem. I mean, I guess it should be 100 minus 90. Okay, but, and then that would be 5 plus 10 plus 30 plus 100. Okay. So, so the only difference between a TLB, the TLB is a very, very small cache that is so small that using hardware, we can check it simultaneously to whatever our lowest level cache is. Okay. So yeah, just back to this picture again. We talked earlier about whether we, the idea is reading from memory. There's a couple of things we could do when we do a read. One is we could say, okay, I'm going to look in the cache. If what I'm looking to read is not here, I'll go to the next level and just keep going until I find it. But now the issue is if you go and you find it, let's say what you're looking for, you went looking here, it wasn't here, so you found a variable here. Okay, so that's how long it took and you read your value. Would you now copy this page up to here because maybe since you've read it recently, maybe you're going to be reading from that page again. So would you take the time to promote a copy up to here? Maybe you would, maybe you wouldn't. You know, it's an operating system decision. But if you do, it's going to take time. Right? So now we're trying to say, how much time does it take to read? Well, okay, I'm going to walk through here till I find what I'm looking for. Then if I find it, I'm going to start walking it back up to get it, you know, because I think it's least recently used. It's going to be, it's a hot page now or something like that. So if we want to add, we might have to add that time to our access time. And then the one about the writes, the issue about writes, as opposed to reads, if, let me go back to this picture. Suppose there's a variable, okay, so there's two policies we could use for writing. One is, if you go to write to a field that's here, let's say we had a variable called x. X is currently equal to 2. There's a copy of x equals 2 over here. Now if you go to change x, you make x a 3 now. Would you change it here, and write it out to the disk drive? Would you change it everywhere, or would you just change it at the location you're closest to? So that's the difference between the write back policy and the write through policy. Do you write it through all the way to the end, or do you just go to the first one you hit and change it there, knowing if you ever hit it again, you're gonna hit this one first, so do you really need to change it here or not? So what would be the advantage to writing it all over the place? Well, one advantage is if you had a cache coherence situation where this main memory is being shared with another cache on a different processor, then you might want this to have a fresh copy. But you could save time if you just go to the spot where you want to change it, just change it there and leave the remaining layers alone. But if you do that, suppose you ever decide to take a page from here and move it up, you have to pick a page to write on top of. And what if the one you're writing on top of has made changes to its data? Then you'd have to say, okay, now I'm going to copy this one back to here, get all the changes, then copy the page up to the new spot. So that could make this page shuffling take a lot of time. So you kind of have to take into account how you want to do your writes. Do you write them at all levels? If you do, that's going to make, how long would every write take? Suppose you decided to have a policy that says if I change a variable, maybe it's in my TLB, maybe it's in my small cache, maybe it's in my big cache, maybe it's in my main memory, maybe it's on my disk drive. But every time I do a write, I'm going to write it everywhere. How long would every write take? It would take the whole, it would take this thing, 5 plus 10 plus 30 plus 100. Every time you write a variable, because you got to write it everywhere. So all writes take a lot of time, and all these caches are slowing you down. So you have to decide, do you want to just write it to the spot where you find it, which would make it take, maybe this amount of time, or maybe this amount of time, or maybe this, But then the downside is, if you only write it to the place where it exists and leave all the pages, all the levels behind you not updated, the downside is every once in a while you're going to take a page from memory, bring in a page from disk, bring it into memory. You're going to be writing on top of a variable that has been changed. So you may have to copy that block back to memory before you bring one in, and now it makes your page swapping take longer. So somewhere there'll be some price for it. So when you go to take into account, should I add this cache memory to make memory access faster, you do have to take into account reads versus writes. Reads are easy. You're just reading a value. You don't have to worry. The first one you find, you read that value. The values behind it will match, and that's okay. But when you're writing, you have to decide how you want to do your writing. And that will get added into your calculation. How long does a write take? And then, the other thing is, if you do reads, and you go walking through your memory and you find the location where it is, do you now also want to promote the page up to make, because you believe future reads are going to come from that same page and you could save time. If you do promote the page up, that could take time too. And actually, copying a page to memory, let me just go back to the very beginning of these slides. Copying a page to memory would actually be faster than reading from a field. So suppose, for example, this is again a small version of memory. But suppose when we want to write to either nibble 1, nibble 2, nibble 3, or nibble 4, I had to put a number between 0 and 3 here to pick which one. Suppose we have the concept of a page. Well, what is a page? A page is a larger group of data. So suppose I decided to make a page size of 2 nibbles. So this is one page, and this is a second page. To decide which page, if I was going to write a page worth of data, so I'd have to have 2 nibbles. So I have 2 nibbles of data here, and I want to either write it to these 2 nibbles or these 2 nibbles. I would have an MAR that has a 0 or a 1. I would have just one wire that opens up all 8 of these, or another wire that opens up these 8. And then I could take these 8 bits and copy them over at once. So it actually, the bigger the bulk of data, as long as you keep doing powers of 2, the bigger the bulk of the data is, the less time it takes to copy a page over. Bigger chunks of data get copied over faster than smaller chunks of data. So that's just, a side thing about paging. Yeah, so those were the right policies, and then, so yeah, so just some of the questions, somewhere you're gonna tack on the cost of, how you decide to handle your rights. How you decide to handle your reads, if you read into memory and you wanna take time to promote the pages to come up, you may have to pick which page are you going to write on top of. If the page you're writing on top of has been modified, you can't just write on top of it, you'll lose the modification. So sometimes they'll use a dirty bit, a page will have a bit that says, oh, this page has been changed since it got promoted up to a higher level of memory. So if you're gonna write on top of that page, you have to copy its value back to the backing page.